Okay, let's talk about gas. Well, not really that kind of gas, but, well, we might talk about that a little bit. But in this case, gases. So, three states of matter, the main ones we talk about, solids, liquids, and gases. This is the one we're talking about, gases. How it works, something called Kinetic Molecular Theory. I'm going to simplify this a little bit for you, but these points you want to know, it makes this whole unit make a lot more sense. First idea. Matter is composed of teeny particles, molecules or atoms, and the space between them, which we'll just call volume, it's the space, is huge compared to the size of the particles themselves. So if we've got a container of air, or even of whatever, if you've got an atom, we blow it up to the same size as my fingernail, the next atom will be about the same distance as 2 football fields away from my finger. That's how much empty space is between atoms, yet still feels solid when we interact with something. But almost all the space we interact with is empty space. Even more so when we're talking about gases. Less so with solids. And all these molecules are in constant motion. We're talking about this with heat and energy and temperature, that every single particle is always moving. It's got kinetic energy. The greater the kinetic energy, the greater the temperature, the faster they're moving on average. Last thing, when those particles are colliding back and forth in the container, we're pretending or assuming that there's no loss of energy. This isn't quite true, but it makes the math work out way, way easier. So pretend no loss of energy when things collide with each other. It's like a bouncy ball that always goes up and down to the same height every single time. No loss of energy from any kind of friction. Okay, got those? Cool. So we need to know what is pressure, because pressure is going to come into play a lot with this kind of stuff. So it's created when at a certain temperature, a certain amount of gas and gas particles occupy a certain amount of space. Which sounds really, really drab. But basically, when there are particles bouncing around in an enclosed container, that causes pressure. So in relation to, that stands for kinetic molecular theory, the pressure is going to be greater, this is important, when there's more collisions happening, and lower when there's fewer collisions happening. So let's pretend that someone's trying to break in and steal stuff from your house. If you want to cause more pressure to try and stop him, and you're throwing pens at him to stop him, you could throw 1 pen at him per second, which would have a little bit of force or pressure to try and slow him down. Or, instead of 1 pen, 1 particle, you could throw 100 pens per second at him, which would cause a lot more pressure, a lot more force on the intruder. Same idea if you've got a lot more particles in a container, they're causing a lot more pressure on the sides of that container, increasing the pressure. If we go back 1 second, the same thing would happen also if they're moving faster. So if I'm throwing that pen at 4 miles an hour or at 40 miles an hour, it's going to make a big difference. So if those particles are moving slowly or more quickly, it's going to change the amount of pressure that we have going on inside that container. All right, gas units. Well, different types of pressure we're talking about. We need to know what different units we use for pressure. Most common one around the world is usually probably atmospheres. We also shorten it to ATMs. Not like the kind you get money out of, but ATM is in atmospheres. The pressure you feel on you, which you actually don't feel on you, but technically there's 1 atmosphere of pressure on you being pushed on you from all around by all the air particles against you. When you dive down in a pool, if you get deep enough and it feels like it's smushing in your head, that's more than 1 atmosphere because the water pressure is more than the air pressure. Another common one is mmHg. It's not mh, but that stands for millimeters of mercury. So that's a very common one in Europe. Just like we use millimeters of, not millimeters, we use inches of mercury here in the US, but we're pretty much the only one that does. Another one is used as pascals, which gets shortened to PAs, and torr. So these are the main 4 we're going to use this year. And again, if you have different units, we have to know how we can make them equal and how we can change between them. So 760 torr is equal to 1 atmosphere, is equal to 101,325 pascals. FYI, this isn't on the slide, but you may want to jot it down. Millimeters of mercury is the exact same number as torr. So 1 torr equals 1 millimeter of mercury, 760 torr equals 760 millimeters of mercury. So all of these units and a few more are also on the back of your periodic table. The green ones I have in class or the white ones you were given. Just like any other conversion, we can do dimensional analysis. Let's try a couple. Okay, so if they're asking for how many millimeters of mercury would you have if you had 4.5 atmospheres of pressure, again, you start with what you're given. They gave us 4.5 atmospheres of pressure, so we start with 4.5 ATMs. We don't want ATMs though, so of course it's going to cancel down here, and we need to get to millimeters of mercury on top. So we put them up there. Now these numbers, back periodic table tells you that 1 atmosphere equals 760 millimeters of mercury, or we also see it on this last slide. Remember, torr millimeters of mercury are the same, so 760 of these equals 1 atmosphere. And hey, atmospheres will cancel, we'll be in millimeters of mercury. That's our answer, so we got to do the math of 4.5 times 760. Gets us our answer of 3,420 millimeters of mercury. Cool. Not too bad, hopefully. Okay, see if you can try this one. How many pascals are in 2,139 millimeters of mercury? Pause it, try it, see if you have the right answer. So again, we're starting with 2,139 millimeters of mercury. We put that to start with. When you do, hopefully you got one of these answers. After you solve it, you should have gotten the red one. So 101,325 pascals in every 760 millimeters of mercury, getting you 285,177 pascals. Hopefully that makes sense. That's why we got that. Okay, let's do one more. How many atmospheres are in 1, 2, 3, 4, 5 pascals? Here are your options again. Give it a shot, see what you get. Okay, so hopefully you've unpaused now and you've got an answer. Hopefully you came out and you got green, 0.12187 atmospheres. We have to go that many decimal places when you actually do it, but just to be safe, the more you have in the middle of your work, the better off you are. Should look something like that for your work. If it didn't, see where you went wrong and figure out why. Okay, 2 important things to know when we're doing any of our gas law calculations coming up here. They must always be in Kelvin for your temperature. Fahrenheit won't work, Celsius won't work, it's got to be in Kelvin. You cannot have a negative temperature when you're doing how much energy an atom has. Atoms have to have positive amounts of energy. And we're going to talk about STP. That stands for standard temperature, which is 0 degrees Celsius. You want to know that. And standard pressure, which is 1 atmosphere. Now it could be in any units, but it's still going to be equal to 1 atmosphere of pressure. Okay, first of our 3 laws, Boyles Law. Boyles Law states that pressure and volume have an indirect relationship. That means they change opposite to one another. So if one goes up, one goes down. The other one goes down, the other one must go up. And if you change the volume of a gas, it has an effect on the pressure. So as the volume decreases, pressure goes up. As volume increases, pressure must go down. Knowing that general thing will be useful. So just note, this is confusing later, it only applies if you have the external pressure. If you have a container here and you squeeze on the outside of it, that's the pressure we're talking about, not the internal pressure of atoms inside of the balloon or container. Internal will be the exact opposite of that. This is your Boyles Law formula. Pressure 1 times volume 1 equals pressure 2 times volume 2. Let's try a practice one. Okay, so if a gas has a pressure of 3 atmospheres and a volume of 75 liters, The volume is then increased to 300 liters. What is the pressure of the gas at this volume? So we know this is pressure 1 because atmosphere is one of our pressure units. We know this is volume 1 because liters is our volume. And another liters once it's increased to this, so we have P1, V1, and then we have V2 and not P2. So we need to solve for V2. So you need to multiply and then divide by this one. You should get 0.75 atmospheres. If you don't do that, let's take a look at your math and see what you're doing a little bit different. Okay, second one. Gas has a volume of 18 liters, pressure of 0.5 atmospheres. Volume's then compressed to 2 liters. What's the pressure of our gas? Same idea, but now we're solving for a new pressure. And you should hopefully get, hopefully you paused it and you solve for 4.5 atmospheres. Now let's do a real life example. If you have a sealed empty milk carton at 1 atmosphere, which is our standard atmospheric pressure, with a volume of 1 gallon, which is about 3.79 liters, and you rapidly compress the milk carton to a volume of 0.5 liters, what is the pressure of the air inside the milk carton? So again, pressure and volume, Boyles Law, should be one of these answers. Give you a second to pause and try it. You then should have gotten the pink one. Second question is, if the cap's a little loose, what's going to happen? Pause, think about it, come back. Your answer should have been something along the lines of, a little loose is going to blow the cap off, because all that pressure inside is now way higher than it was before, and way higher than the outside pressure, or it's going to just go and let all the air out, depending on how the cap is, how securely it's on there. You get smushed in like you would if the cap's not tight. Okay, second one, Charles' Law. A little quicker now. At a constant pressure, so pressure doesn't change now, but volume and temperature have a direct relationship, which means that one goes up, the other one goes up. One goes down, the other one goes down. Again, temperatures have to be in Kelvin. So as temperature goes down, volume goes down. Temperature goes up, volume goes up. This one, we've got volume 1. Whoops, there should be 1s there. We missed it. Okay. Should be volume 1 over temperature 1 equals volume 2 over temperature 2. Just write them in on your own. That'll be your formula we're going to use here. Okay, so here's our example. You have a 1 liter balloon at room temperature, which is 298 degrees Kelvin. Nope, no degrees. You take it outside where it's only 273 Kelvin. What is the new volume of the balloon? So we have 1 volume and 2 temperatures. And you need to cross multiply and divide when you do these to get one of these answers. When you cross multiply and divide, you should be getting a little lower volume than you had before. Should make sense, right? Our temperature went down a little bit, so our volume should go down a little bit. That's what our direct relationships means. Okay? Here, no words, just numbers. We have a V1, T1, no V2, we have a T2. Pause and solve. What do you get? And think about if you can figure out if it should go up or down just based on the numbers. Okay, hopefully you realize the volume should be going up because the temperature went up. And your volume comes out to, actually you should really Bill say some of these are not reasonable. The answer's got to be pink or purple or lavender, whatever that color is. 4.9 liters. Okay, here's one more. Try and go through it. Whoops. Bottom came out first. Pause it, try and solve for the right color / number. You hopefully should be getting the blue one. Our last one's pronounced, it looks like Gay-Lussac's law. It's pronounced Gay-Lussac's law. I'm going to pause here and do another little mini video on the end of this one to go through our last law and how you can know which one's which.